42. That is the number of times Kilauea has erupted in its current cycle. And if that were the whole story, we would not be here tonight. The whole story is this. Every single one of those 42 eruptions has been larger than the one before it. Not occasionally larger, not randomly larger. Consistently, progressively, mathematically larger, as if something underneath this island is not releasing pressure, so much as collecting it. Geophysicist Stefan Burns has been watching the tilt data, the seismic swarms, the sulfur dioxide readings, and what he sees written across all three is a question that serious scientists are now asking in serious rooms. What exactly is this volcano building toward? Tonight we follow that question all the way down, through restructured magma plumbing, through a mantle plume that may be surging, and into territory so unexpected it involves the sun itself. Stay with us until the end, because the data is pointing somewhere, and it has not slowed down once. Subscribe and follow along, because 42 episodes is only the opening act. The magma system remains locked in its escalating state. The plumbing beneath Kilauea is threaded with pressure that has not fully released since 2018, and the recharge from below continues arriving on a schedule written long before any monitoring network existed to read it. Something is climbing, not randomly, not chaotically, but with the kind of deliberate, escalating rhythm that makes volcanologists set down their coffee and stare at their screens a little longer than usual. Kilauea volcano, sitting on the big island of Hawaii, has just entered its 42nd eruptive episode in its current active cycle. 42. And before you file that number away as just another geological statistic, let me stop you right there, because the number itself is almost not the point. The point is what that number is doing. It is not staying flat. It is not bouncing around randomly. It is climbing. And in the world of volcano science, a system that keeps climbing without resetting is a system that is telling you something. To understand why this matters, you need to understand what a normal volcanic cycle actually looks like. Most volcanoes, when they erupt, follow a kind of natural exhale. Pressure builds, magma forces its way up, the eruption happens, and then, critically, the system deflates. It breathes out. Tilt meters, which are instruments so sensitive they can detect the ground tilting by a millionth of a degree, show the volcano essentially relaxing after each episode. The pressure drops. The ground subsides slightly. The system returns closer to where it started. That is the reset. That is what volcanoes are supposed to do. Kilauea is not doing that. Geophysicist Stefan Burns has been tracking the tilt data across these episodes, and what he describes is something researchers have started calling a ratchet effect. Picture inflating a balloon, but every time you let some air out, you never fully deflate it before pumping more air back in. Do that 42 times. The balloon is now significantly more inflated than when you started, even though you have been releasing pressure along the way. That is the model Burns is describing for Kilauea's shallow magma chamber right now. Each eruption releases some pressure, but not enough. The post-eruption deflation never fully returns to the previous baseline. And the inflation amplitude, how much the ground swells before each new episode, appears to be increasing from one cycle to the next. That word, increasing, should stay with you for a moment. The tilt meters are telling us the ground is puffing up more before each eruption than it did before the last one. That means more pressure is being added to the system than is being released. And if you follow that math forward, even just a few steps, you arrive at a question scientists are genuinely struggling to answer. Where does that accumulated pressure eventually go? The seismic data adds another layer to this picture. Before each eruptive episode, Kilauea produces what are called seismic swarms, clusters of small earthquakes generated by magma physically forcing its way through rock. Rock fractures. The ground shakes in tight, rapid sequences. These swarms are normal before eruptions. What is not entirely normal is the density and clustering of recent swarms. Individual earthquakes in isolation are essentially background noise for a volcano like this. But when swarms cluster more tightly, when the fracturing becomes more concentrated and frequent, that is magma telling you it is moving with more urgency, encountering more resistance, or both. Then there is the sulfur dioxide. Every time fresh magma rises toward the surface, it releases gases, and sulfur dioxide, or SO2, is one of the clearest chemical signatures of new, volatile-rich magma ascending from below. Kilauea has been pumping out elevated SO2 across these episodes, and the pattern of that gas output aligns uncomfortably well with the tilt and seismic data. More gas, more ground inflation, more seismic urgency. 3 independent data streams, all pointing the same direction. Now, scientists are careful people. No volcanologist at the USGS is standing at a podium predicting catastrophe. That is not how science works, and it is not what the data is saying, at least not yet. What the data is saying is more subtle and, in some ways, more unsettling. One large eruption episode is noise. 5 is interesting. 42 progressively escalating episodes is a pattern, and patterns in science demand explanation. Stephen Burns frames it this way: the system is not venting, it is compounding. Magma recharge, the rate at which new molten rock is being fed into the system from below, appears to be outpacing the rate at which eruptions are discharging it. The volcano is, in net terms, filling up. Burns is clear that this is his interpretation, not an official USGS position. But the data he is drawing from is real, it is public, and it is difficult to look at without feeling a quiet, creeping unease. Here is the thing about patterns. We are very good at recognizing them in hindsight. Historians of volcanic disasters can often point to the warning signals that were present before a major regime shift: the escalating episodes, the incomplete resets, the building pressure that everyone assumed would eventually just plateau. Sometimes it does plateau. The system finds a new equilibrium and ticks along for decades, but sometimes it does not. 42 episodes in, with each one arriving faster and bigger than the last, the honest scientific question is not, is this dangerous right now? The honest question is, what is this volcano building toward? And to begin answering that, you cannot just look at what is happening at the surface. You have to look at what happened in 2018, when Kilauea essentially tore its own plumbing apart and rebuilt something that nobody has fully mapped yet. The year 2018 did not just produce one of the most dramatic volcanic events in modern American history. It fundamentally rewired a volcano. And the system that came out the other side of that event is not the same system that went in, which means every model, every baseline measurement, every historical comparison we try to apply to Kilauea's current behavior is being applied to a volcano that may have changed in ways we do not yet fully understand. Here is what happened. In 2018, Kilauea's lower east rift zone erupted with extraordinary force. Lava fissures opened in residential neighborhoods. Entire subdivisions were consumed. But the event that geologists found most scientifically significant was happening at the summit, at a crater called Halemaumau. As the lower rift zone drained enormous volumes of magma, the summit lava lake, which had been a stable, spectacular feature for years, began to drop. And then the ground above the emptying magma chamber started to collapse. Not once, not twice. Over the course of weeks, the summit caldera collapsed dozens of times, in episodic lurches, each one dropping the crater floor further and further down. By the time it was over, the summit had subsided by roughly 1.5 miles across and dropped hundreds of meters in depth. The volcano had essentially caved in on itself. Now think about what that does to the plumbing. A magma system is not a simple tank with a single pipe. It is a complex network of chambers, conduits, and pathways carved through rock over thousands of years. When the summit collapsed in 2018, that geometry changed. Conduits that had been open may have been pinched off or sealed by collapsing rock and rapidly cooling lava. New pathways may have formed. The pressure distribution across the entire system shifted in ways that are extremely difficult to model from the surface. Researchers did their best. But the honest acknowledgement from the scientific community is that the post-2018 Kilauea is running on plumbing that has never existed in the modern monitoring era. We are watching a volcano operate through architecture we have never seen before. The tilt data reflects this. Pre-2018, Kilauea's inflation and deflation cycles had a certain character, a recognizable rhythm that monitoring networks had recorded for decades. Post-2018, that rhythm changed. Inflation episodes have become more frequent. The pattern of ground deformation suggests that magma may be accumulating in different configurations than before. Some researchers hypothesize that the recharge is now drawing from deeper sources, feeding into a summit reservoir that is being rebuilt from scratch after being almost completely drained. This is where two competing hypotheses begin to pull against each other. The first is what you might call the rebuilding model. After the massive drainage event of 2018, the volcano lost an enormous volume of stored magma. What we may be watching now, these 42 escalating episodes, is the volcano slowly, incrementally refilling that reservoir. Each eruption is a partial discharge from a system that is still, in net terms, accumulating. The episodes are getting bigger, not because something alarming is happening, but because the reservoir is growing. Think of it as a bathtub, slowly filling with the drain partially open. Eventually, the inflow exceeds the outflow, and the water level rises. The second hypothesis is more uncomfortable. It suggests that the 2018 collapse did not just drain the chamber, it changed how efficiently pressure can be released. If conduits were narrowed or sealed by the collapse, then each eruption is working through a smaller exit than before. Pressure builds faster. Release per episode is less complete. The ratchet effect may not just be about increased magma supply, it may be about decreased discharge efficiency. A bottleneck. And if that is true, then the escalation pattern is not a refilling story. It is a pressure accumulation story. These two hypotheses are not mutually exclusive. Both could be contributing simultaneously. More magma coming in, less efficiently getting out. If that is the case, the trajectory becomes significantly more interesting to track. There is one more variable that rarely gets discussed in casual coverage of Kilauea. Magma is not just liquid rock. It carries gases, water vapor, carbon dioxide, sulfur dioxide, dissolved within it under pressure, much like carbonation dissolved in a soda bottle. As magma rises and pressure decreases, those gases come out of solution. How efficiently they degas determines a great deal about how an eruption behaves. Magma that degasses gradually and completely tends to produce effusive eruptions, rivers of lava flowing calmly downslope. Magma that retains its gases until the last moment tends to produce explosive behavior, because the sudden exsolution of those gases can shatter the magma into fine particles and generate violent blasts. There is no current evidence that Kilauea's magma is trending toward that kind of volatile retention. To be absolutely clear about that. But the structural changes of 2018, the potential bottlenecking of conduits, the possibility of magma spending more time under pressure before finding an exit, these are exactly the conditions that, in theory, could influence degassing efficiency. Scientists are watching. They are measuring. They are being careful. But somewhere beneath all the careful language and measured uncertainty, there is a question that keeps surfacing. If the shallow system is doing something it has never done before, is the driver of that something also new? And to answer that, you have to go much further down. Further than the magma chamber. Further than the crust. All the way down to a column of superheated rock rising from the lower part of Earth's interior. A mantle plume that may not be as steady as we assumed. The Hawaiian Islands exist because of a pipe. Not a literal pipe, but something that functions like one. A column of unusually hot, buoyant rock rising from far below the surface of the Earth, punching through the overlying tectonic plate and melting it from underneath. This is what geologists call a mantle plume, and the Hawaiian hotspot is one of the most studied examples on the planet. The Pacific Plate drifts slowly northwest over this fixed heat source, and as it does, volcanoes form, grow, erupt for millions of years, and then go cold as the plate carries them away from the source. The chain of Hawaiian islands and seamounts stretching across the Pacific is essentially a geological timestamp of this process, each island progressively older as you move northwest, a frozen record of where the hotspot was millions of years ago. What this model implies is that the plume is relatively steady, a constant heat source producing a more or less consistent supply of magma to whatever volcano happens to be sitting over it. Kilauea and its neighbor, Mauna Loa, are currently the most active volcanoes in the chain because they are closest to the hotspot's present position. The magma supply they receive should, in theory, be relatively stable over human timescales. Except the geologic record suggests it is not always that simple. When geologists examine the spacing and volume of material in the Hawaiian island chain over geologic time, they find something interesting. The output is not perfectly uniform. There are periods where more volcanic material was produced, and periods where less was. The islands themselves are not evenly sized or evenly spaced in ways that would suggest a perfectly constant source. What this implies is that the plume may experience pulses, periods of increased flux, where more heat and partially molten material rises more vigorously, and quieter periods where the output dims. These pulses play out over thousands to tens of thousands of years, far too slow to observe directly in a human lifetime. But here is the uncomfortable question. If a pulse is underway, if the Hawaiian hotspot has entered a period of slightly elevated output, what would that look like in the short term? It would look like increased magma supply to the active volcanoes at the chain's current end. It would look like recharge rates that outpace eruption discharge rates. It would look like a ratchet effect, where each episode releases less pressure than the system accumulates between events. It would look, in other words, remarkably like what we are observing right now. This is speculative. There is no confirmed measurement of a current plume pulse. Seismic tomography, the technique of using earthquake waves to image Earth's interior like a CT scan, does give us some picture of the plume's structure, and what it reveals is not a simple straight column, but a more complex branching geometry that varies with depth. Imaging the deep interior is extraordinarily difficult, and the resolution of current tomographic models is not fine enough to detect subtle changes in flux in real time. We simply do not have the instruments to watch the plume the way we watch the summit. Mauna Loa adds another wrinkle to this picture. Kilauea and Mauna Loa sit close enough together that they likely share, or at least tap into, the same deep magma source. Historical records show a loose pattern of alternating dominance. Periods when Mauna Loa is more active, followed by periods when Kilauea is more active, as if the two volcanoes are drawing from a common reservoir that preferentially feeds one or the other at different times. If there is a shared deep surge happening right now, both volcanoes could be affected. Mauna Loa erupted in 2022 for the first time in nearly 4 decades. Kilauea has been erupting almost continuously since 2023. Two of Earth's most powerful volcanoes on the same island, both becoming more active within the same short window. That could be coincidence. Earth is a big, complex system, and coincidences happen. But coincidences that align with a testable model, increased deep supply driving elevated activity across both volcanoes simultaneously, have a way of demanding more careful attention than simple chance would warrant. If the plume is pulsing, the implications extend well beyond Kilauea's current episode count. A sustained increase in magma supply, even a modest one, would mean that the escalation we are watching is not a temporary anomaly that will self-correct. It would mean the system is being driven from below by a process operating on a time scale that dwarfs any human planning horizon. The 42 episodes would not be an aberration. They would be the opening chapters of something much longer. And if the driver goes that far down, it raises a question that sounds almost absurd until you look at the data. Could something from the opposite direction, from above the Earth entirely, also be influencing what we see? The answer is controversial. The science is contested. But the hypothesis refuses to die. And the reason it refuses is more interesting than most people realize. Let us be upfront about something before we go any further. What you are about to hear is not mainstream science. The connection between space weather and volcanic or seismic activity has not been established to the satisfaction of the broader geophysical community. There is no accepted physical mechanism. The correlation studies that exist are disputed, and the forces involved, solar electromagnetic activity versus the titanic pressures of Earth's interior, are so different in scale that most researchers consider the comparison almost category level wrong. And yet, the hypothesis keeps coming back. And the reason it keeps coming back is worth understanding, even if the conclusion remains unproven. Solar cycle 25 is currently approaching its peak. The Sun, which operates on roughly an 11-year cycle of magnetic activity, is producing more solar flares, more coronal mass ejections, and more intense geomagnetic storms than it has in roughly 2 decades. A coronal mass ejection is essentially a massive bubble of charged plasma erupting from the Sun's surface and racing through space at millions of miles per hour. When one of these hits Earth's magnetic field, it compresses and distorts that field, inducing electrical currents in the ground, disrupting satellites and power grids, and producing auroras at unusually low latitudes. Stephen Burns and a small number of researchers have pointed to correlations between periods of intense geomagnetic storm activity and upticks in seismic and volcanic events. The hypothesis they propose is that the influx of charged particles and the electromagnetic disturbances associated with major solar events could influence stress states in Earth's crust, potentially acting as a trigger for systems that are already near a threshold. Not a cause in this framing, but a trigger, the way a small vibration can trigger an avalanche in a snowpack that was already primed to slide. The mainstream objection is straightforward and powerful. The energy involved in even the largest geomagnetic storm, as it interacts with Earth's crust, is orders of magnitude smaller than the forces driving magma through rock. We are comparing a whisper to a freight train. The idea that electromagnetic modulation from a solar event could meaningfully alter the pressure dynamics inside a magma system is, for most geophysicists, a bridge too far. But the people who find the correlation interesting are not necessarily arguing for a direct energy transfer mechanism. They are asking whether electromagnetic effects could influence fluid dynamics in partially molten rock, whether subtle changes in electrical conductivity or ionic behavior in magma and groundwater systems could, in a system already at the edge of a threshold, nudge behavior in ways that show up in the timing of eruptions. The question is not, can the sun melt rock? The question is whether a system poised at a knife's edge might be sensitive to influences we typically dismiss as too small to matter. The honest answer right now is that we do not know. The datasets are not long enough. The correlations that researchers like Burns cite are intriguing, but not definitive. Other researchers examining the same historical record find the signal unconvincing. This is how contested science looks before it resolves, messily, with smart people disagreeing about what the data actually shows. What is not contested is this: we are at solar maximum. Kilauea is in an unprecedented escalation pattern, and the geomagnetic environment is unusually disturbed. Whether those facts are connected or merely concurrent is a question that honest scientists answer with We do not know yet. But the overlap in timing is real. And in a system we are still trying to understand from the inside out, ruling out potential influences too quickly has historically not served us well. Even if the sun turns out to be entirely irrelevant to what Kilauea is doing, the escalation pattern still exists. The tilt data still shows a ratchet. The seismic swarms are still clustering with unusual frequency. The SO2 is still elevated. The system is still compounding. And if space weather is not the driver, then something else is. Something that has been building in the accounting of energy and magma beneath this island for years. Something that is, in the language of physics, out of balance. Every volcanic system runs on a budget. It sounds almost mundane when you put it that way. A budget, like something you might discuss over a spreadsheet on a Thursday afternoon. But the budget a volcano runs on is not measured in dollars or euros. It is measured in cubic kilometers of molten rock, in gigapascals of pressure, in the thermal energy of a planet that has been cooling since it formed 4.5 billion years ago and has not finished yet. Magma flows in from below, fed by the mantle plume, processed through deeper storage zones, and pushed toward the surface through a network of conduits carved through solid rock over timescales that dwarf anything human civilization has experienced. Magma flows out through eruptions, through slow surface lava flows spreading across the landscape, through gases bleeding into the atmosphere, in plumes visible from orbit. In a system that is roughly in equilibrium, in a volcano that is doing what volcanoes in a stable state do, the input and output balance over time. The pressure stays within a recognizable range. The eruptions follow a rhythm that, while never perfectly predictable, has a character that experienced researchers come to know. The resets are real. The system exhales, and then it inhales again, and the cycle continues. What Stefan Burns and a growing number of researchers are describing with Kilauea's current behavior is a system where that budget has gone meaningfully out of balance. Input is exceeding output. More magma is arriving from below than is being discharged through eruptions and surface flows. And because the excess does not simply vanish, because energy in a physical system cannot disappear, it can only be stored or transferred. It accumulates. Pressure rises. The stored energy in the system increases with each incomplete reset, compounding across each successive episode like interest accruing in an account that nobody is drawing down fast enough. This is not a metaphor or a dramatic flourish. This is thermodynamics, one of the most rigorously tested frameworks in all of physics, applied to a geological system. The first law does not negotiate. Energy goes somewhere. And right now, in Kilauea's shallow magma chamber and potentially in storage zones considerably deeper, the somewhere is increasingly apparent. The ratchet model, when you sit with it long enough to think through the energy accounting in full, becomes genuinely sobering in a way that the surface-level description of escalating eruptions does not quite capture. Each of the 42 episodes has released energy. That is not in dispute. Lava fountaining hundreds of meters into the air. Lava flows advancing across the caldera floor. Sulfur dioxide billowing into the atmosphere in quantities detectable from space. These are real, measurable discharges of the pressure that built before each event. The question is not whether energy is being released. The question is whether the release is keeping pace with the accumulation. And the tilt data, episode after episode, suggests it is not. If every cycle ends with the system slightly more pressurized than it was at the equivalent point in the previous cycle, if the deflation after each eruption consistently falls short of returning to the pre-inflation baseline, then over 42 cycles, the compounded surplus of stored energy could be substantially larger than any single episode's contribution would suggest. You are not talking about one eruption's worth of accumulated pressure. You may be talking about the net excess from months of continuous imbalance, layered and compounded across nearly 4 dozen incomplete resets. Where does that energy physically reside? The shallow magma chamber beneath Kilauea's summit is the most obvious answer, and the tilt data confirms that it is inflating in ways consistent with ongoing pressurization. Tilt meters positioned around the summit record the ground swelling upward and outward as magma pushes against the walls of the chamber from within. This is standard volcanic monitoring, well understood and carefully tracked. But shallow chambers are not the only storage architecture in a complex volcanic system, and focusing exclusively on the summit reservoir may give an incomplete picture of the total energy inventory. Deeper storage zones, bodies of partially molten rock sitting lower in the crust, or pooled at the boundary between the crust and the mantle, can also accumulate significant volumes of magma. These zones are considerably harder to detect with surface instruments, harder to model with current computational tools, and much harder to monitor in anything approaching real time. If substantial volumes of magma are pooling at depth, close enough to the active system to contribute to its pressure budget, but not yet close enough to the surface to drive immediate eruptive behavior, then the summit tilt meters, as sensitive and valuable as they are, may be showing us only the most visible portion of a much larger accumulation. The full inventory may be considerably more substantial than the surface measurements alone can reveal. Then there is the question of volatiles, which is where the energy accounting problem intersects with a separate and distinctly more consequential line of concern. Magma is not simply liquid rock. It is liquid rock saturated with dissolved gases, primarily water vapor, carbon dioxide, and sulfur dioxide, held in solution by the enormous pressure of the overlying rock column. The behavior of those gases as magma rises toward the surface determines, to a remarkable degree, how an eruption actually unfolds. As magma ascends and the confining pressure decreases, the gases begin to exsolve, to come out of solution, expanding rapidly, the way carbon dioxide fizzes out of a soda bottle the moment you release the cap. In a volcanic system with open, efficient conduits, wide pathways that allow magma to move relatively freely from depth to surface, this degassing happens gradually and progressively. The gases escape incrementally as the magma rises, the pressure releases in a controlled and continuous way, and the result is typically effusive eruption behavior. Lava that flows rather than explodes, fountaining that is dramatic but not catastrophically violent. But in a system where the conduits have been narrowed, partially sealed, or structurally reorganized, as the post-2018 plumbing beneath Cape Kilauea may well have been, given the scale of the collapse event and the complexity of the rebuilding that followed, the picture changes in important ways. Magma that cannot move freely toward the surface spends more time at depth under sustained high pressure. During that time, the dissolved gases remain in solution rather than exsolving gradually. The magma becomes, in effect, increasingly gas-charged, a pressurized mixture waiting for the decompression event that will allow rapid exsolution. When that event finally comes, when the magma finds or forces a path to the surface, and the pressure drops suddenly, the exsolution does not happen gradually. It happens fast. And gas-rich magma undergoing rapid, uncontrolled exsolution does not flow quietly downslope. It fragments. It accelerates. It drives explosive eruption dynamics that are categorically different from the effusive behavior that characterizes Kilauea's current activity. This is the scenario, not the certainty, not the prediction, but the theoretical trajectory that keeps volcanologists watchful, even as they are scrupulously careful to avoid language that might be mistaken for an alarm. There is no current evidence that Kilauea's eruptions are shifting toward an explosive regime. The activity right now is effusive. Lava is fountaining and flowing in the mode that has characterized this volcano throughout the modern monitoring era. Dramatic and hazardous in its own right, but not in the category of the violently explosive events that the geological record shows this same volcano producing in earlier periods of its history. The scientists monitoring Kilauea are not standing at podiums, warning of imminent catastrophe. They are doing their jobs carefully, measuring everything they can measure, and being honest about the difference between what the data currently shows and what the theoretical framework of energy accumulation suggests is worth watching. But the geological record has a way of providing context that no single monitoring cycle can supply on its own, and the context it provides for Kilauea is not entirely comfortable. This volcano has not always been the relatively gentle, effusively erupting system that drew tourists to the Hawaii Volcanoes National Park in the 20th and 21st centuries. The stratigraphic record, the layers of deposited material preserved in the rock and soil across the Big Island, contains clear evidence of past explosive eruptions at Kilauea, events that sent ash columns high into the atmosphere and deposited material across large portions of the island. Those events happened during periods when the volcano's plumbing was configured in ways that promoted volatile retention and rapid decompression rather than gradual, controlled degassing. The conditions that produced them are not identical to current conditions, but they are not entirely alien to them either. Volcanoes are not simple escalation machines that climb steadily toward a predictable outcome and then stop. They are nonlinear systems, subject to the same threshold dynamics and sudden regime shifts that characterize all complex physical systems driven far from equilibrium. They plateau, or they transition, and the difference between those two outcomes is not always visible in the data until the transition is already underway. The data, right now, does not show a plateau. The tilt is not leveling off. The gas output is not declining. The seismic swarms are not becoming less frequent or less densely clustered. The episode count is not slowing. What the data shows across every independent measurement stream available to the monitoring network is a system that is still climbing, still accumulating, still compounding, still failing to fully reset between cycles. And that trajectory raises a question that is difficult to confine to the boundaries of one island or one volcano or one monitoring network's dataset. It raises a question about what else might be moving at the same time, on the same planet, and whether the convergence of accelerating systems that we began to notice several parts ago is telling us something that no single data stream, examined in isolation, is equipped to say. The budget is out of balance. The accumulation is real. And somewhere in the accounting, there is an entry that has not yet been posted. Something has been happening to Earth's magnetic field for the past few centuries, and only in the last few decades have we had the satellite technology to watch it happen in detail. The magnetic field, that invisible shell generated by the churning of liquid iron in Earth's outer core, is not a fixed, stable structure. It moves. It varies in strength. It has reversed polarity hundreds of times throughout Earth's history, flipping north and south in events that play out over thousands of years. And right now, by multiple measurements, it is weakening. Not dramatically, not in ways you would feel on a Tuesday morning, but measurably, consistently, and in the judgment of several research teams, faster than the recent historical average would predict. The South Atlantic anomaly is the most dramatic expression of this weakening, and it is worth spending a moment with because most people have never heard of it, despite the fact that it is one of the more consequential geophysical features on the planet. It is a region stretching roughly from South America to Southern Africa, where Earth's magnetic field is significantly weaker than the global average, weak enough that satellites passing through it experience elevated radiation exposure and occasional instrument glitches. Spacecraft operators know to expect anomalies when their hardware crosses this zone. The International Space Station passes through it regularly, and astronauts on board receive measurably higher radiation doses during those transits. The anomaly is not new, but it has been growing and drifting over the past several decades, expanding its footprint across the South Atlantic in ways that are clearly visible in the satellite data. And based on some recent analyses, it may be in the process of splitting into two distinct lobes, a structural change that, if confirmed, would represent a significant shift in how the anomaly is organized and how it interacts with the broader field. Meanwhile, at the opposite end of the planet, the magnetic North Pole has been drifting at an accelerating rate for decades. This is not a new phenomenon. The pole has been moving since we first started tracking it in the 19th century, but the speed of that drift has increased substantially in recent years. The pole is currently moving faster than at any point in the modern measurement era, racing across the Canadian Arctic towards Siberia at a pace that has forced the agencies responsible for navigation systems to update the world magnetic model ahead of their normal schedule. That model underpins everything from smartphone compass apps to aviation navigation systems, and updating it early is not a trivial decision. It reflects genuine urgency in keeping our maps of Earth's magnetic geometry accurate enough to be useful. None of this is secret or suppressed. The scientific agencies tracking these changes, including the National Oceanic and Atmospheric Administration and the European Space Agency, publish their monitoring data openly and update it regularly. Researchers debate the implications, but the measurements themselves are not in dispute. The behavior is unusual by recent historical standards, and the mechanisms driving it are rooted in the dynamics of Earth's outer core, that vast ocean of liquid iron whose circulation patterns generate the magnetic field in the first place. When those circulation patterns shift, the field shifts with them, and right now, something in the core's behavior appears to be producing a field that is reorganizing itself in real time. In 2026, this matters in ways that go beyond the purely academic. Solar maximum is currently intensifying the radiation environment surrounding Earth. The Sun is producing more high-energy particle events, more coronal mass ejections, more geomagnetic storms than it has in roughly 2 decades. Earth's magnetic field is the primary barrier between the surface and that radiation. When the field is strong and stable, it deflects the vast majority of incoming charged particles, funneling them toward the poles where they produce auroras rather than damage. When the field is weakening, particularly in regions like the South Atlantic anomaly, where it is already thin, that protection is reduced. More radiation reaches lower altitudes. Satellites are more vulnerable. And the overall electromagnetic environment experienced by Earth's surface systems becomes more complex and more energetic than during quieter periods. Here is where intellectual honesty requires a careful and deliberate distinction, because this is the kind of territory where it is easy to connect dots that should not yet be connected. There is no verified direct link between Earth's magnetic field changes and Kilauea's volcanic escalation. The physical connection between surface magnetic field strength and the dynamics of magma systems operating several miles underground is not established by any mainstream scientific framework. These are separate phenomena, driven by separate processes, operating on genuinely different timescales. The magnetic field changes we are discussing play out over centuries and millennia. Kilauea's current escalation cycle has unfolded over a period of months to years. Linking them directly, without a clear mechanism, would be speculation dressed as science. And that is not what we are doing here. But the reason to mention both phenomena in the same conversation is not to manufacture a false causal connection. It is to observe something broader, something more honest, and something considerably harder to simply dismiss. Multiple large-scale Earth systems are showing unusual behavior simultaneously. The magnetic field is weakening faster than recent historical norms suggest it should be. The magnetic poles are drifting at speeds that have surprised the researchers tracking them. Solar activity is running hotter than early cycle forecasts predicted. One of Earth's most carefully monitored volcanoes is exhibiting a 42-episode escalation pattern that has no clear precedent in the modern instrumental record. Ocean heat content in the Pacific has been running at record levels. The jet stream has been exhibiting unusual behavior. Each of these facts, examined in complete isolation, carries its own range of explanations stretching from the entirely mundane to the genuinely significant. Examined together, they form a picture of a planet in which several major systems are accelerating at the same time. Whether that acceleration is meaningful convergence, systems influencing each other through mechanisms we have not yet identified, or whether it is simply random coincidence that pattern-hungry human minds are weaving into a false narrative, is a question that science will need considerably more time and data to answer. The honest position right now is uncertainty. Not alarmed certainty, but not comfortable dismissal either. The human brain is, at its most fundamental level, pattern recognition hardware. It is what kept our ancestors alive on a planet full of things trying to eat them. When multiple independent indicators point toward accelerating change across different Earth systems, even the most cautious and rigorously trained scientific observers tend to sit up straighter, look at the data again, and ask whether the convergence is telling them something their existing models have not yet captured. That instinct is not paranoia. It is not motivated reasoning. It is the beginning of good science, the moment when the anomaly becomes too consistent to file away as noise and demands to be treated as a potential signal. The question then becomes, how do you investigate a potential signal that spans multiple systems, operates across different scales, and resists the kind of controlled experimentation that laboratory science depends on? You cannot run a control trial on a planet. You cannot rewind Earth's history and replay it without the magnetic weakening to see what happens. What you can do is gather more data, build more sophisticated models, and apply the most powerful pattern recognition tools available to the problem. And in 2026, the most powerful pattern recognition tools available are not human analysts working through spreadsheets on a Monday afternoon. They are artificial intelligence systems trained on geophysical datasets of a scale and complexity that no individual researcher could process in a lifetime. What happens when you point those systems directly at this kind of multi-system acceleration and ask them to find the structure in the noise? The answer is not yet complete, and the researchers running these models are appropriately careful about what they claim. But the early signals emerging from AI-assisted Earth system monitoring are already surfacing questions and correlations that human analysts, working alone, were simply not equipped to ask. And some of what those systems are flagging, when applied specifically to Kilauea's escalation sequence, is raising eyebrows in rooms where eyebrows are not raised easily. That is where we are going next. Science in 2026 looks different than it did a decade ago, and nowhere is that difference more consequential than in the monitoring of complex nonlinear natural systems. The instruments have gotten better. The datasets have gotten larger. The satellite coverage has become more comprehensive, the ground-based sensor networks more dense, and the computational power available to researchers more formidable than anything the previous generation of volcanologists could have imagined sitting at their desks in the 1980s. But perhaps the single most transformative development in Earth system monitoring over the past several years is not a sensor or a satellite at all. It is software. Artificial intelligence, specifically machine learning models trained on large geophysical datasets, has entered the field of volcanic monitoring with a speed and impact that has surprised even its most enthusiastic proponents. These systems do not get tired. They do not carry the weight of prior assumptions about how a particular volcano is supposed to behave. They do not have a career investment in a specific theoretical framework that might subtly bias how they interpret an anomalous reading. They process continuous streams of seismic, geodetic, and geochemical data, and they look for patterns purely, relentlessly, without ego, in ways that human analysts, reviewing the same data in the compressed and interrupted time of a working day, might not notice until the window for early action has already closed. Researchers have begun applying these tools to Kilauea's current activity sequence, and the early results are generating significant discussion in geophysical circles. Machine learning models trained on historical eruption precursors, fed decades of data from Kilauea itself as well as comparable volcanoes around the world, are flagging the current pattern as unusual. Not unusual in the narrow sense that any single individual parameter is elevated beyond a threshold. Unusual in a deeper and more structurally significant sense. Multiple parameters are elevated simultaneously, and they are co-evolving, moving together, influencing each other, tracking in coordinated ways, in patterns that historical data suggests are correlated with significant volcanic transitions, rather than with the simpler escalation and plateau cycles that tend to resolve without dramatic change. To understand why that distinction matters, you need to spend a moment with what scientists mean when they use the phrase nonlinear regime shift, because it is one of those technical terms that sounds abstract until you understand it. And then it sounds like something you should have been worried about much earlier. Most of us think about change in intuitive, proportional terms. Push a system a little, and it responds a little. Push it harder, and it responds more, in roughly the same direction, at roughly the same rate. This is linear thinking, and it works reasonably well for a large number of everyday phenomena. It does not work well for volcanic systems. It does not work well for climate systems, or ecosystems, or financial markets, or any of the other complex, interconnected, feedback-driven systems that actually govern most of what matters in the physical world. Volcanic systems, in particular, have a deeply nonlinear character. They can absorb enormous amounts of pressure and perturbation over extended periods, months, years, sometimes decades, with relatively little visible change at the surface. The ground inflates slightly. Gas output ticks upward. Seismicity increases modestly. To a casual observer, and sometimes even to an experienced one, the system looks like it is doing what it always does, just a little more so. And then, when some internal threshold is crossed, when the pressure in the chamber exceeds the mechanical strength of the confining rock, or when the volatile content of the magma reaches the point where exsolution becomes inevitable, or when a structural element of the plumbing that had been holding gives way, the system shifts. Not gradually, not proportionally, abruptly and dramatically into an entirely new mode of behavior. Mathematicians and physicists have a precise term for this kind of transition. They call it a bifurcation. The system occupied one stable state. It now occupies another. And the passage between those two states was not a slow drift, but a sudden reorganization that may have taken hours or even minutes to complete after years of invisible preparation. Volcanoes are among the most compelling and consequential examples of bifurcation dynamics in the natural world. They can sustain escalating cycles of activity that, observed from inside the timeline, look as though they could continue indefinitely at roughly the same level, and then, at some threshold of pressure or geometry or volatile loading, the fundamental nature of the activity changes. Sometimes, that transition is relatively contained, a shift in eruption location, a change in lava output rate, a new fissure opening in an unexpected area. Sometimes the transition is considerably more significant, involving a step change in eruption intensity or style that resets the hazard calculus for everyone in the surrounding region. The geological record of Kilauea itself contains evidence of past transitions between effusive and explosive regimes, periods when the volcano that today produces relatively calm lava flows was instead generating violent explosive eruptions that deposited ash across the island. Those transitions happened before. The conditions that drove them were not entirely unlike the conditions being monitored right now. The particular challenge of nonlinear systems is that the threshold, the specific point at which bifurcation occurs, is almost never visible in advance. You cannot look at a pressure gauge and read off the exact number at which the system will shift. What you can do, and what decades of mathematical research into complex systems has established, is look for the signatures that nonlinear systems tend to produce as they approach a threshold. These signatures are subtle, but they are real. Systems near a bifurcation point tend to show increased variability in their behavior. Fluctuations become larger and less regular. They show slower recovery from small perturbations. Nudge the system slightly, and it takes longer to return to its prior state than it would have earlier in the cycle. And they sometimes show a kind of flickering, an irregular oscillation between states that can precede a full transition the way summer lightning precedes a storm. Researchers have a formal name for this cluster of behaviors. They call it critical slowing down. And AI systems specifically trained to detect these mathematical signatures in geophysical data streams are now pointed directly at Kilauea's monitoring network. What they are finding is not a certainty, and it would be irresponsible to present it as one. Probabilistic models in geophysics are not oracles. They cannot tell you that an eruption will happen on a specific date, or that a specific threshold will be crossed at a specific pressure level. What they can do is characterize the distribution of likely outcomes given the current trajectory of the system, essentially asking, across all the historical cases that looked most like this one, what happened next, and in what proportions. That is a structurally important question, even when the answer is uncertain, because uncertainty is not the same as ignorance. A model that tells you the probability distribution is weighted toward continued escalation rather than spontaneous plateau is giving you genuinely useful information, even if it cannot tell you exactly when or how the escalation resolves. The scientists running these models are careful with their language, and understandably so. They understand the weight of responsibility that comes with making any public statement about a volcano sitting above a populated island that draws hundreds of thousands of visitors each year and anchors a significant portion of Hawaii's economy. They are not predicting catastrophe. They are not sounding evacuation alarms or issuing declarations that the island is in imminent danger. They are doing what science does at its most valuable and its most honest. They are looking at the data without flinching, building the best model the current state of the field allows, and reporting transparently what that model says about the range and weighting of possible futures. That is not alarmism. That is the job. And what the models are saying right now is that the uncertainty is weighted toward continued escalation rather than spontaneous de-escalation. The system does not show the mathematical signatures of a volcano approaching a natural equilibrium. The energy accounting does not close in a way consistent with a system moving toward balance. The pattern recognition does not match the historical sequences that resolved quietly, that simply ran out of steam and subsided back to baseline without incident. It matches more closely the sequences that preceded something. We began this investigation with 42 eruptive episodes and a ratchet that would not release. We followed the thread down through structurally altered magma plumbing that nobody has fully mapped, into a mantle plume that may be delivering more material than it used to, through the contested and unresolved territory of space weather connections, and out across a planet where multiple large-scale systems, the magnetic field, the solar cycle, the volcanic record, are simultaneously moving faster than their recent historical baselines suggested they should. We applied the most sophisticated pattern recognition tools our civilization has yet produced to the accumulated data and asked the only question that ultimately matters: what comes next? The honest answer is that nobody knows. Earth is not a machine with a user manual, and Kilauea has humbled researchers before. It may de-escalate in ways that no current model anticipated. It may continue exactly as it has, episode after episode, for years to come, never crossing the threshold that would force a regime shift. It may do something else entirely, something outside the envelope of historical analogy that the models were trained on. Science is not prophecy, and anyone who tells you otherwise is selling something. But science is also not silence, and the data is not silent. The tilt keeps rising. The gases keep climbing. The seismic swarms keep clustering with a frequency and density that marks a system under mounting internal stress. The resets keep failing to fully close, cycle after cycle after cycle. 42 episodes in, with each one arriving larger than the last, the system shows no credible sign of the plateau that would allow the people watching it to finally exhale. Somewhere below this island, in plumbing rebuilt from a collapse that nobody fully modeled, fed by a source that may be delivering more than it ever has in the modern monitoring era, a vast and ancient and entirely indifferent process continues doing what it has done for hundreds of thousands of years. It builds, it compresses, it accumulates. It does not read the monitoring reports. Toward, that is the question that will toward. That is the question that will define the next chapter of this story. And episode 43, whenever it arrives, will not come as a surprise to the instruments. It will come as the next entry in a sequence that has not yet found its ceiling, written in the language of heat and pressure and time, in a ledger that has been accumulating entries long before anyone was around to read them.